Okay, I hope I'm audible to all students who are attending this lecture for the ISI MSQE entrance. In this lecture, I intend to start with the discussion for the ISI PEB 2021 paper. Okay, we have done the ISI PEA 2021 paper. Remember, MSQE has two exams. One is the PEA exam, which is objective type, and one is the PEB exam, which is subjective type. So this is the subjective paper. This is the subjective paper for the MSQE entrance at ISI, and we intend to discuss the 2021 paper. Okay, so let's look at the first question. Let's look at the first question. Every question is for 30 marks. You can see the first question, which has two parts. The first part is for 10 marks. The second one is for 20 marks. Okay, so let's read the question and then we can solve it. Let f be a function which maps real numbers to real numbers, be a continuously differentiable function which has at least three distinct zeros. Now, all students can recall, when do we say that x is a zero of the function f? X is a zero of the function f if f of x is equal to 0. If you put the value of x in the function and as a result you get the value of the function as 0, you can conclude that x is a zero of the function f. Let g be a function which maps r to r, be defined as follows. G of x is given to us as e to the power x by 2 times f of x for all x belonging to real numbers. The question is asking us, prove that g has at least three distinct zeros. That's part A, which is for 10 marks. And part B, prove that the function f plus 2f dash, where f dash is the first order derivative, has at least two distinct zeros. So we need to show that g has at least three distinct zeros, and we need to show that f plus 2f dash has at least two distinct zeros. So let's come to the whiteboard and let's solve this question. Remember, it's a subjective question. We don't have any MCQs here. Okay, so we have started our discussion of ISI PEB paper for 2021, and we are looking at question 1 in this lecture. So what we are given, I'm just quickly writing it for reference. We are given that f is a function which maps r to r, is a continuously differentiable function. It is a continuously differentiable function which has at least three distinct zeros. Which has at least three distinct zeros. Okay, and I'm just quickly writing note that x is a zero. X is a zero of the function f if f of x is equal to 0. We are given that g is a function which maps r to r, be defined as g of x is equal to e to the power x by 2 times f of x for all x belonging to real numbers. The first part to this question is asking us, prove that g has at least three distinct zeros. Prove that g has at least three distinct zeros. Okay, so let's quickly first of all solve the first part and then we'll solve part B to this question. Okay, so first of all, we are given that g is a function which maps r to r, and the function g of x is e to the power x by 2 times f of x. Now, all students can see that e to the power x by 2 will always be positive because e is always positive. You raise a positive base to any power, it will always be positive. So I can say that e to the power x by 2 is always a positive quantity, right? For all x belonging to real numbers. So therefore I can say what? Therefore we can say that if beta is a zero of the function f, that is f of beta is equal to 0, then beta will also be a zero of g. Since this term is always positive, if x equal to beta is a 0 for the function f of x, then x equal to beta will also be a 0 for the function g of x. So I can write that, therefore, I can write it like this, that beta is a 0 of g if and only if, double implication means if and only if, beta is a 0 of the function f. You can clearly see that since g of beta will be equal to e to the power beta by 2 into f of beta. Now e to the power beta by 2 will always be positive. So this equal to 0 implies f of beta is equal to 0. If I say that beta is a 0 of g, that means g of beta is equal to 0. What is g of beta? E to the power beta by 2 times f of beta. Now e to the power beta by 2 is always positive because it's positive base raised to any power. So for the whole term to be equal to 0, f of beta must be equal to 0, which implies beta must be a 0 of the function f also. So what can I say? I can say that therefore both the functions f and g, have exactly the same set of zeros. Both the functions f and g have exactly the same set of zeros. So now I can write here that since f has at least 3 distinct zeros, since we are given that f has at least 3 distinct zeros, therefore g will also have at least 3 distinct zeros. Suppose I say that f has 3 distinct zeros, let's say beta 1, beta 2, beta 3. They are distinct, which means beta 1, beta 2, beta 3 are not equal to each other. If I say that f has 3 distinct zeros, then since we have shown that both the functions will have exactly the same set of zeros, if in the question we are given that the function f has 3 distinct zeros, then automatically function g will also have at least 3 distinct zeros. So we have proved it. Okay, I'm quickly revising. We were given the function g which maps r to r. G of x is e to the power x by 2 times f of x. E to the power x by 2 is always positive. So g of x is equal to e to the power x by 2 times f of x. The function g will have a 0 only when f has the same 0. So if I say that beta is a 0 of g, if and only if beta is also a 0 of f, because g of beta equal to 0 implies e to the power beta by 2 times f of beta is equal to 0, which implies f of beta is equal to 0, since e to the power beta by 2 is always positive. So if beta is a 0 of g, then beta must be a 0 of f also. Since in the question we were given that f has 3 distinct zeros, therefore by that logic, g will also have at least 3 distinct zeros. Okay, so we have shown part A. Now I'm erasing part A. And now let's look at what part B is asking us. Erasing this part off. Let's look at part B. Okay, so part B is asking us now prove that the function f plus 2f dash has at least two distinct zeros. Now this is a good one. We need to prove that f plus 2f dash has at least two distinct zeros. Okay. Now, somewhat I need to first of all get f plus 2f dash. And we are given the function g. Let's differentiate the function g and let's see what do we get. So we were given that g is the function which maps r to r, and we were given that g of x is e to the power x by 2 times f of x for all x belonging to real numbers. If I differentiate this, g dash x will be what? If I apply the product rule of differentiation, it's e to the power x by 2 times f dash x plus f of x into e to the power x by 2 ka derivative is e to the power x by 2 times 1 by 2. So within this, guys, I can take e to the power x by 2 as common. And I'm left with f dash x plus f of x by 2. Okay. And if I take 2 also outside, suppose I do it like this, e to the power x by 2, suppose I divide by 2 outside. If I divide by 2 outside, I'm going to multiply by 2 inside to nullify the impact. If I am dividing outside by 2, I have to multiply the term in the bracket by 2 to nullify the impact. So this is going to be 2f dash x plus, if I multiply this by 2, it becomes f of x. So if you carefully see, my g dash is equal to e to the power x by 2 times f plus 2f dash. And again, guys, you can see now it has the same story as part A. Clearly, e to the power x by 2 is strictly positive for all x belonging to real numbers. You can see that this term is always positive. So what can I say? I can say that therefore g dash has exactly the same set of zeros. G dash has exactly the same set of zeros as f plus 2f dash. Okay, it will have the same set of zeros as f plus 2f dash. Okay, now let us show that f plus 2f dash has at least two distinct zeros. Let's show that. So first of all, let us see how many zeros will g dash have, because guys, we have already shown that g dash is going to have the same set of zeros as f plus 2f dash. So let us now find out how many zeros will g dash have. Okay, now from part A, we have shown that g also has three distinct zeros. So if I erase this part off, I hope all students have written down till here. Okay, so erasing this part off, I can write that from part A, we proved that G has three distinct zeros. So let me take them. I can say let beta 1, beta 2, and beta 3 be three distinct zeros such that I can say beta 1 is less than beta 2 is less than beta 3. Suppose I take three distinct zeros of the function g. Okay. So beta 1, beta 2, beta 3, I say that these are the three distinct zeros such that beta 1 is less than beta 2 is less than beta 3. Okay. Now, if I pick up beta 1 and beta 2, now, since g of beta 1 and g of beta 2 both are equal and they are equal to 0, and g is continuous, G is continuous. Therefore, by Rolle's theorem, what can I say? All students have done, we have done the Rolle's theorem in our mathematical methods for economics part 1 course, in our lectures on implications of continuity and derivability. We have done this in our lectures on continuity and derivability theorems in our mathematical methods for economics part 1 course. So by Rolle's theorem, what can I say? If g of beta 1 and g of beta 2 are equal and the function g is continuous, I can say that by Rolle's theorem, there exists a I can say there exists a C1 belonging to beta 1 to beta 2, open interval beta 1 to beta 2, such that g dash of C1 is equal to 0. That is, I can say C1 is a 0 of the function g dash. So I picked up beta 1 and beta 2. And you can see that beta 1 and beta 2 are not equal. Beta 1 is less than beta 2, but g of beta 1 and g of beta 2 both are equal to 0 because beta 1 and beta 2 both are zeros for the function g. And since my function g is continuous, by Rolle's theorem, there exists a C1 lying in the interior of B1 to B2 such that g dash of C1 is equal to 0. When I say that g dash of C1 is equal to 0, it means that C1 is a 0 of the function g dash. So I've got 1 0. Now I can repeat the same process between beta 2 and beta 3. So if I erase this particular part off, I can repeat the same process between beta 2 and beta 3. So I can write that also, since beta 2 is less than beta 3, but g of beta 2 and g of beta 3 both are equal to 0, since beta 2 and beta 3 are also zeros for the function g, and g is continuous. Again, I can invoke the Rolle's theorem. I can say that by Rolle's theorem, there exists a C2 belonging to the open interval beta 2 to beta 3 such that g dash of C2 is equal to 0. So I can write that is C2 is a 0 of the function g dash. So guys, we have shown that the function g dash has at least 2 distinct zeros. Therefore, g dash has at least 2 distinct zeros, that is C1 and C2. C1 is also a 0 because g dash of C1 is equal to 0. C2 is also a 0 because g dash of C2 is equal to 0. So the function g dash has 2 distinct zeros. And since I had said that g dash has exactly the same set of zeros as f plus 2f dash, since g dash has at least 2 distinct zeros, I can say that therefore f plus 2f dash also has at least 2 distinct zeros. So I can write this on the top that since g dash has at least 2 distinct zeros, since g dash has at least 2 distinct zeros, therefore f plus 2f dash also has at least 2 distinct zeros. Hence proved. So we have proved that f plus 2f dash is going to have at least 2 distinct zeros because we have proved that g dash has exactly the same set of zeros as f plus 2f dash, and we have shown that g dash has at least 2 distinct zeros by Rolle's theorem. So this was our solution for part. Okay, so hoping all students have understood this. This is where I intend to stop in this particular lecture. Okay, the objective of this lecture was to discuss with all students the first question, which was in the ISI PEB paper for 2021. Okay, in the next lecture, I will be taking up question 2 for discussion. in the next lecture, I intend to take up question 2 for discussion. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.